Okay, thank you very much, Matthew, for the introduction, and thanks also to the UK Fluids Network for arranging this prize. So I'm Rowan Braxton. I'll talk to you today about some of the work I was doing for my PhD, supervised by Andrew Wynne and Jonathan Morrison. We were working in the Aeronautics department at Imperial College. So the thesis was entitled Stochastic Modeling and Feedback Control for Efficient Bluff Body Drag Reduction. So I'll first of all go through some of the sort of background, some of the motivation for this work in bluff body drag reduction. I'll talk about our experiments that we had in aeronautics at Imperial. I'll then talk about so open loop forcing, of a tough turbulent bluff body wake. I'll look at some low order stochastic models that we developed for the flow. I'll then discuss some of the feedback control strategies that we developed for drag reduction purposes, and then finally conclude. So just to give some motivation to the problem. So road vehicles and road transport are responsible for approximately 20% of global CO2 emissions. And really, these vehicles are essentially blunt bodies. So in terms of their shape, they're generally aerodynamically fairly inefficient if you were to compare them to, say, an aircraft, due to this sort of blunt rear end that they have. And this shape really stems from practical and to some extent aesthetic constraints on the geometry. So maybe if you wanted to make them much more efficient, you could make them much longer, make this into some sort of extended aerofoil type shape, but really that's not practical. So this motivates using other active feedback control methods by which we can modify the flow without making large geometric changes. And that's the work that I was pursuing during the PhD. So these three-dimensional bluff body wakes, of which those behind road vehicles are an example. We're talking about wakes that are highly turbulent Reynolds numbers, so Reynolds numbers order 10 to the 6. And the drag on the body in these cases is predominantly form drag. So it arises due to the high pressure at the front and the low pressure at the back due to this large separated wake region. Although the drag force on the body manifests due to this pressure difference, it can also be related to what's going on in the flow. So in terms of a sort of energy budget, you can say that the power expended in moving the body through the fluid has got to be equal to the total dissipation over the wake. So in this way, you can think that really the structures and the features within the wake are somehow responsible directly for the drag force and the pressure forces on the body. Now, these sorts of three-dimensional bluff body flows, as was originally proposed by Roelle and Takens, they undergo the bifurcation route to turbulence. So we start off with a symmetric steady flow at very low Reynolds numbers, and that undergoes a series of bifurcations in the flow. And as I'll show you, these bifurcations result in notable coherent structures, even in the high Reynolds number flow, which gives us something to target as a flow control strategy. And two of these structures in particular, which I'll discuss now, are the static symmetry breaking and the quasi-oscillatory vortex shedding within the wake. So the first of these structures, what I'll call the static symmetry breaking of the flow, occurs as a pitchfork bifurcation at very low Reynolds numbers. So these, if we think now, this is essentially a plan view of a simplified car model, here visualized in the work by Grondemange and Cadeau. And at low Reynolds number, say 310, you initially have, because of the symmetric geometry, you have a symmetric and steady laminar wake behind the body. As you increase the Reynolds numbers, in this case to 365, this bifurcation leads to the flow transitioning from being a steady and symmetric wake to one which is steady but asymmetric. This is a symmetry breaking in the flow. And this feature leads to an increase in the drag because this asymmetric wake leads to a lateral force on the body and increased circulation that's being shared into the wake. But what's important to note is that this asymmetry, although it's clearly visible at these very low Reynolds numbers, when we go up to the high turbulent Reynolds numbers that are typical of real road vehicles and for our experiments, this asymmetry persists in the flow. So this is a sort of static PIV snapshot of our wake at Reynolds 10 to the 5. And you can see this same asymmetry persists, which leads to an average lateral force on the body, and we believe is responsible for part of the drag that the body experiences. And this phenomenon of this symmetry breaking is quite general to a number of three-dimensional bluff body flows, in terms of including axisymmetric flows or double backward-facing steps, and it's really quite a general feature. So the second sort of coherent structure and feature of these three-dimensional wakes I'll discuss is the vortex shedding. So after this initial bifurcation that I showed on the previous slide, we have a steady but asymmetric wake. As you increase the Reynolds number further, the flow undergoes this time a Hopf bifurcation, and we now have both an asymmetric but unsteady wake with a characteristic oscillatory frequency at Struhl number 0.2. So this leads to a further increase in the drag relative to what you might expect if the flow remained steady. And this unsteadiness persists up to the high Reynolds numbers that we're interested in for practical road vehicle flows. And really, you can think of this, although the geometry of the flow is somewhat different, it's similar in many ways to the sort of canonical vortex shedding behind the cylinder that you're likely familiar with. So, given that these three-dimensional turbulent flows have these particular coherent features, and that these features can, in some ways, be related most likely to the drag, we essentially targeted an approach in which we hope to regulate these particular coherent structures, these particular features in the turbulent wake, in the hope that this leads to a drag reduction. So we want to understand firstly how we can regulate these structures via some sort of control input from the body to the flow, whether we can measure these structures effectively via some surface-mounted measurements. Then the purpose was to develop some low-order models to describe the dynamics of these structures, how they develop in the flow, and how our inputs and our measurements are related to these models. And then finally, the aim was to use these models to try and design effective but also practically implementable feedback control strategies that would regulate the features and hopefully lead to drag reduction as a result. So I'll quickly go over the experimental setup that we had. So this is what's known as the Achmed body, which is a reference sort of simplified car geometry, which is widely used in this sort of research area. And because the dimensions of this, the ratios are similar to those used by many other authors, we can compare results and so on. So we tested this in the wind tunnels at Imperial College at Reynolds number order 10 to the 5 to get a fully turbulent flow. We had the model mounted on a plate, which is slightly raised off the floor, so we have minimal sort of boundary layer interference underneath the body. And then our measurements, we had 6-component force balance underneath, so we could measure the lateral forces, the drag accurately. And also we had an array of pressure measurements on the back. And these pressure measurements on the back were used for feedback control purposes as our measurement, and also to analyze what's going on in the flow. And then the final crucial feature, in order to have actuators with which we could try and control these features in the flow, we had these dynamic flaps. So these white surfaces here, essentially they're parallel with the sides of the car body. And these are driven internally by motors, which allow us to either operate them with a static offset, to give a sort of static lateral force, or they can be oscillated up to the sort of relevant frequencies that we require to try and control the features within the wake. So just to make that a bit clearer, so these flaps are mounted on the back, facing backwards. As I'll discuss later, we can either mount these flaps on the sides. So this is an image of the rear face of the body. We can either mount them at the sides, or we can mount them at the top and the bottom faces, either one of those. And when I discuss later input from the flaps, I'll refer to the angle theta. And this is with the two flaps moving together in essentially an anti-symmetric manner. So when one moves inwards, the other one moves outwards. I'll talk about the pressure modes on the back, M. So because the particular features in the flow that we're trying to look at, essentially anti-symmetric features, we look at essentially a pressure gradient, either laterally or vertically on the base of the body, denoted by M. And then we'll also look at the forces, so the streamwise drag force or the lateral forces. So the first part of the investigation was to look at the behavior of the flow in both an unforced and in a case where we force in an open loop manner. So we firstly look at the unforced behavior of the flow. So this is essentially the lateral side-to-side pressure gradient along the base of the body. And if we look at a time series, we see this very clear sort of bistable flipping signature. So this is the manifestation of that original pitchfork bifurcation in the flow that leads to this sort of static asymmetry. So at any one time, the flow is clearly asymmetric, and there's an accompanying lateral force that occurs at the same time. And if the body is well aligned with the flow, this will be randomly switching between these two different equal and opposite asymmetric configurations. And if we look at the frequency spectrum associated with this time series, you see a lot of low frequency energy and this -2 exponent corresponding to this bistable flipping process. Also, perhaps much less clear, at roughly Struhl 0.2, so this vortex shedding frequency, you see a kind of corner frequency in the spectrum. So this shedding behavior is still present in the wake. It's much clearer if you were to look at velocity measurements, for example. But this is still somehow present in these pressure measurements that we take. If you compare that now with vertical pressure gradient on the base, so looking at the sort of top-down asymmetry, you see that there's no longer this bistable flipping behavior. This low frequency energy isn't there because there's no longer this bistable flipping. But again, you see this slight imprint from the vortex shedding, this sort of corner frequency at Struhl number 0.2. So the first sort of forcing we can do with our flaps is to just position them at static angles, sort of static offsets, and see how that interacts with these large-scale features in the flow. So what we find if we position the flaps at various different angles theta in a sort of anti-symmetric manner, we're able to preferentially select the sense of the asymmetry that the flow exhibits. So if we have theta equals 0, we have this sort of bistable wake, so that in here the pressure gradient flips between roughly, let's spend equal time in a positive or a negative pressure gradient configuration. And as we skew the flaps one way or another, we preferentially select going towards one or the other configuration. And you can visualize that with these are time-averaged streamlines of the wake behind. And really, actually, the pressure that's induced by the curvature of the flow around the flaps is consistent with what you'd expect for this particular flow structure in the wake. So one sees essentially a low-pressure vortex in the recirculation region here, which corresponds to the low pressure you'd expect from the curvature of the flow over this flap. And similarly, you have a higher pressure on this side of the base, which corresponds with the higher pressure also from the curvature over the flap, deflecting the flow outwards. So as well as this static forcing, we can also force the flaps harmonically. So here we force the flaps at a wide range of frequencies and also a number of different amplitudes. And then we evaluated the frequency response between that harmonic flap input and the response of the pressure gradient on the base, so extracting that particular harmonic component from the pressure gradient. So what one sees when doing that with these lateral flaps, you see at very low frequencies you have a relatively large response. So this corresponds to sort of repeated induced flipping of the wake between these two asymmetric configurations. And then as you increase the frequency, this response dies off somewhat. Until then at higher frequencies again, so this is Struhl 0.2, you have again a large response. In this case, the flaps are exciting with the oscillatory vortex shedding of the flow. They're exciting that particular feature. And if we look here at the relative change of the drag force, so this is the streamwise force coefficient, the drag coefficient, we see at low frequencies there's a small change, a small increase over the baseline case, which is 1 here. And then as we get to the point where we're exciting with the vortex shedding, we see a very large drag increases. So clearly this large-scale unsteadiness is very bad in terms of the drag on the body. A final feature, which I'll come back to later, we see at these sort of intermediate frequencies, we see a sort of sharp trough in the response, in the measured response that we see. And this has implications, as I'll discuss later, for feedback control. So if we now perform the same experiment, but with the flaps at the top and bottom of the body, and we look at the vertical pressure gradient, we see a somewhat similar response. So at low frequencies, we're able to sort of skew the wake upwards or downwards. And then again, at the sort of stool number 0.2, we see this large measured response as we excite the vortex shedding in the flow. And again, we see very large drag increases when we do that, as well as this trough in the response, accompanied by a large phase, sort of phase angle decrease at these intermediate frequencies. So, just to summarize the effect of our open loop forcing, we see that the unforced wake is laterally bistable, and it has and sort of monostable in the up-down configuration. It has these very weak vortex shedding imprints that we can measure with the base pressure, but that if we force the wake at this same frequency, we see a very strong excitation of the flow. We can use the lateral flaps to select the sense of this static asymmetry in the flow in the lateral sense, as well as this strong interaction with the shedding. And our measurements, using just these surface-mounted features, our measured response is quite strong, but we have this sharp dip at intermediate frequencies. So given our understanding of these features of the wake and our interaction with them, we can try and develop some sort of low-order models, which we will then use for feedback control. So essentially, because these features in the wake, these large-scale coherent structures, initially arise from these bifurcations at very low Reynolds numbers, we can follow a modeling approach originally suggested by one of my colleagues, George Regas at Imperial, where we model these features of the wake in the turbulent regime as the equation that governs that original bifurcation, but with the addition of some stochastic term, which here is in a phenomenological sense modeling the effect of turbulence, the small-scale turbulent fluctuations that are present in the high Reynolds number flow. And then we can also incorporate some input term which corresponds to the effect that our flaps, our control inputs are having. So this sort of model is a stochastic differential equation, essentially, where this is just like a white noise input, and then we have some deterministic part and some control input. So if we look first at that static symmetry breaking feature of the wake, this arises from a pitchfork bifurcation. So if we modify that more general model on the previous slide, and we take some single metric R, which quantifies somehow this asymmetry of the flow, we can say that it's governed by this equation, which governs a pitchfork bifurcation, with the addition of some term which quantifies the influence that our flaps are able to have on this flow feature, and then the addition of this stochastic term. So given such a model for the flow, we can first say, okay, well, what sort of behavior does that predict, and is it consistent with what we see in our experimental observations at high Reynolds numbers? So firstly, given this equation, we can compute what's the expected probability distribution for this metric R. And for this system, which is one-dimensional, you can compute what's known as the Fokker-Planck equation, which gives the steady-state probability distribution corresponding to this stochastic equation. And this gives us a sort of bistable expected probability distribution for this metric. We can also look for, if we put in a harmonic theta, so theta is some sine omega t, and we look for harmonic solutions in R, then we can try and obtain an equivalent frequency response. And one finds if you do that, you expect we expect the system to act a bit like a sort of first-order low-pass filter. So a strong response at low frequencies, and then some roll-off that's at a frequency corresponding to this parameter alpha. So now comparing that with our experimental measurements, high Reynolds number, we can see that we get this, as I was showing before, we get this bimodal distribution of our pressure metric, M, which corresponds very nicely with the right parameters to that bimodal distribution that one can obtain analytically from the Fokker-Planck equation. So essentially, by comparing these probability distributions and seeing how the skewness of the distribution changes with theta, you can extract the parameter b here, and also the ratio of the parameters sigma and alpha. And then, by also looking at the frequency responses that I was showing before, we can also try and obtain the time scale defined by alpha, and also tau, which is a time delay here. So by this combination of the probability distribution and the frequency response, we can obtain the parameters that fit this model quite closely to the data. If we want to follow the same sort of modeling approach, but now for the vortex shedding in the flow, then we can take instead the parameter x to be complex. So now we have a similar equation, but it's with complex parameters for some complex x that somehow describes the amplitude of the vortex shedding in the flow. And if you split that into real and imaginary parts, you have some amplitude, which will have some equilibrium value defined by these parameters, and then also some stochastic component, and some component which is dependent on the forcing input u. And then we have the phase of this mode x, which increases linearly with time according to some alpha, and then also some stochastic component. So this describes a sort of noisy oscillatory process. And this is similar to previous approaches that have been used for other absolutely unstable flows. So if we look at the sort of predictions one can obtain from that stochastic model for the oscillatory process, you see it gives us sort of noisy oscillations. And looking at the frequency spectrum of that, you get this sort of broadband peak. And this is qualitatively similar to what you would observe if you were to put a hot wire, for example, into the particular portion of the flow in which the vortex shedding was manifesting. But in terms of this model, it might give us a good qualitative description. But what we're really interested in is what does it tell us for feedback control and how we might apply our feedback control approaches that I'll discuss. So really, for that model, if you put in some harmonic input and then you measure, say, just the real or imaginary parts of the output, you find that it behaves almost perfectly like a second-order linear system. So this is just like a mass spring damper system, essentially. So you get some resonant behavior at the frequency defined by this parameter, and then also this phase decay. And as we'll see, this ties in very well with what we observe from the real input-output response for the turbulent flow. So these models it's kind of nice that we can have these models that describe sort of qualitatively quite well what the flow is doing. But the real purpose is to describe in some slightly more accurate way the input-output behavior so that we can go on to design feedback controllers. So if we think that our low-frequency behavior, which corresponds to either the sort of flipping of the wake between these two bistable configurations, or a sort of slow deflection of the wake, if we think that acts like some sort of first-order low-pass system, which is consistent with our first model, and then if we think about this behavior around Struhl number 0.2, well, we can think that acts like a sort of linear second-order system, which is resonant at that frequency. You find if you have these two models with the right parameters, and you model your response as the sort of addition of these two different sets of dynamics, then one finds that you can match very closely this observed sort of frequency response that we find from our experiments. And it's this, by adding these two different responses together, you essentially get a cancelling out of the dynamics at some sort of intermediate frequencies, and this gives this sharp trough in the frequency response. And this is something that is sometimes typically seen in certain feedback control problems, and it's this trough is called what known as right half plane zeros, which cause particular challenges for feedback control design. So having developed these models for the flow and seen how we can add them together to give a sort of complete input-output response, we can now go on to design some feedback control strategies. So we think about two different approaches, really. So in the first approach, we can try and directly regulate this sort of bistable flipping, this sort of static asymmetry of the wake. And this requires us to use the flaps to have good control at sort of very low frequencies, at DC, so that we can change the wake from one which is somewhat asymmetric to one that's more symmetric. And we'll apply that using flaps mounted on the two edges in the lateral dimension. The alternative approach is to try and regulate the vortex shedding, so some of the unsteadiness in the flow. And this requires us to sort of suppress oscillations if we can. And it requires control no longer at DC, at low frequencies, but at the Struhl numbers around 0.2. And we'll apply that using flaps at the top and bottom in the sort of vertical dimension. So the challenge now is to design some controller K, which operates through our actuators, which also have some dynamics, in order to try and suppress either the sort of static asymmetry that we're measuring here or the oscillations in this measurement. So if we firstly look at that first control approach, where we're trying to change the static behavior, if we do some sort of analysis of our model, we find that really what we need is we need quite a high gain at low frequencies. So this is a bit like balancing a pendulum almost. You need to be able to push it back if it starts to move away. So we need some sort of good high gain at low frequencies. And then we also want to avoid these interactions that we were seeing with the vortex shedding at higher frequencies. So this requires us to design some K which has some high gain here and then rolls off very quickly. So to see what sort of results that gives, what we have here, we have a time series in which we have the natural dynamics of the wake measured up to here, and then at t equals 0, we turn our controller on. And you can see that at this time point, we transition from a wake which is flipping between these two asymmetric configurations to one which is, on average, more symmetric. And we find if we look at the drag force as well, we see a pretty rapid decrease in the drag, which corresponds to, well, in this case, 2.4%. And although that might seem quite a modest sort of drag reduction, it was very encouraging for us that this drag reduction was actually energetically efficient. So we can measure the energy saved by reducing the drag and the particular velocity, and also measure the electrical power that we supply to the actuators. And in this case, the actuators consume less than a quarter of the power that is saved. So really this tells us that both the particular actuators that we've chosen are efficient in terms of regulating the flow, but also that trying to target this particular feature of the flow is somehow a fundamentally efficient approach to use. But to understand why we can't do better than that sort of 2.4%, we can look at some of the limitations. So we find if we try a sort of hierarchy of controllers that are increasingly aggressive with increasingly higher gains, we can make the flow increasingly symmetric. So this is just sort of the modulus of that pressure gradient on the base. So we can make the flow increasingly symmetric, but we increasingly apply more oscillations within the wake. So although we suppress this low frequency energy in the spectrum, we put a lot more energy in at higher frequencies due to these sorts of unwanted interactions with the vortex shedding or with other features of the flow. And these fluctuations are generally detrimental to the drag. So having seen that, we can now look to apply the other approach in which we target the fluctuations directly. So this is the approach which is applied to try and regulate the vortex shedding. So one approach to doing this is to use what's known in control theory as the sensitivity function. So if one thinks about all these unwanted fluctuations in the flow as being a sort of external disturbance to our system which we're trying to control, when we apply feedback, there's a particular transfer function which gives us the measured response corresponding to these disturbances. And this is the sensitivity function. So the idea is we can design some controller K that makes this sensitivity function less than 1 over some particular frequency range at which we want to try and attenuate the disturbances. And this is the approach that's been applied by Amy Morgan's group quite a number of times. In order to do that, we use what's called H-infinity synthesis, where we design a particular frequency response for this sensitivity function, and then this H-infinity synthesis procedure automatically designs a controller to try and achieve that particular response. So, for example, here's one such sensitivity function response in which we design it to have a trough here, close to Struhl number 0.2, and then in order to do that, it's forced to also have peaks elsewhere. So when this log of s is less than 0, we have attenuation or expected attenuation in that frequency range. And when it's greater than 0, we'll have amplification of disturbances. So we can sweep through a range of these different controllers, varying various parameters and various sort of shapes of this frequency response. And what we find when we do that is that we're able to, as we hoped, we're able to suppress fluctuations in various frequency ranges. So if we look at a comparison between the controlled and uncontrolled spectra here, we find we're able to significantly suppress fluctuations, for example, in this Struhl number 0.2 range, where we think that the shedding is operating. But naturally, as was also anticipated, we're forced to increase fluctuations in other frequency ranges. And after trying a very large number of these controllers, sort of 150 or 200, I think we applied experimentally, we find we're actually never able to reduce the drag by this approach. So just to briefly explain why perhaps this is, there's something in control theory known as the waterbed effect. So this is essentially a fundamental limitation of linear control systems, where if we reduce fluctuations in one frequency range, we're obliged to increase them in another. And it's very difficult, actually, to determine whether, when we do this, are we achieving some beneficial effect here in terms of the drag and a detrimental effect there. And it's very difficult to decouple these effects. So at this stage, it's unclear whether this approach is one which has promise to be effective or not. Okay, so to conclude, these sorts of turbulent bluff body wakes, which are typical of road vehicles, they have a lot of coherent structures which can be linked to the drag that the body experiences, and we're really motivated to try and reduce this drag. On a simplified car model, we can strongly interact with these structures and then form models that describe their dynamics and how they respond to the input and output behavior. And then these models allow us to try and design feedback control strategies that we implement practically, which can achieve efficient drag reduction in some cases, but in other cases is unable to. Okay, thank you very much.
As you know, we started a little late, so it's time for one question. I guess I have one, which is, what would it take to apply this to a real car?
So I think the things that we did, we could scale up to a real car. It would probably become practically quite expensive because we had these a lot of sort of intricate motors and this sort of thing. I think the main challenge is that implementing these, constructing this within the existing sort of manufacturing processes that the cars have, it starts to become quite a headache for the manufacturers. So you really have to have enough motivation there in terms of the drag reduction to make it worthwhile. But I think physically there's nothing that says that we couldn't do it.
Okay. Great. Well, thank you very much, Rowan.
Right, thanks.
Good afternoon, everyone. Welcome to my presentation. My name is Simon Chen. So I did my PhD in University of Liverpool from 2013 to 2017. My supervisor was Dr. Mofango Botola. And then now I'm working as a postdoctoral research fellow in National University of Singapore. So this talk summarizes my 4-year PhD study in Liverpool, which is the drop impact phenomena with complex fluids on heated and soft surfaces. So drop impact is a classic subject of interfacial hydrodynamics. Normally people are looking at the drops of simple fluid impacting on flat isosomers surfaces. Here I'm playing with some complicating factors. For example, I changed the properties of the fluid. I used the Lang-Newtonian fluids. I mix the water and the polymers to get polymer solutions. And also I tried different types of substrates. For example, I tried heated surface with a temperature above the Leidenfrost point. And also I tried soft surfaces which undergo permanent or temporary deformations during drop impact. So I'd like to divide my talk into 4 sections. First, I will talk about the symmetry breaking Leidenfrost drops, and then the viscoplastic Leidenfrost drops, followed by the impact of viscoplastic drops on viscoplastic surfaces, finally the drop impact on spherical soft surfaces. So first, the symmetry breaking Leidenfrost drops. So first, a brief introduction about the dynamic Leidenfrost phenomenon. So if you have a droplet which impacts on a heated surface, and a very thin vapor layer will be formed due to rapid evaporation, which is working as an elastic cushion, which separates the droplet fluid and the heated surface. And finally, the droplet may observe to bounce off the surface. And for example, this is a recorded movie of a typical Leidenfrost drop impact. And in previous studies, people found that at high impact vapor numbers, the Newtonian drops actually bounces much lower compared to the Lang-Newtonian drops. So these are the data for the polymer solutions. And this has been explained by a reduction of the energy dissipation during the drop impact process. For example, if you look at this equation, if you have less energy dissipation, you will have a higher maximum bouncing height. But that is really the Lang-Newtonian effect? Question mark. So our job is to systematically investigate the rheological effects on the energy distribution during drop impact. And the fluid choice principle is presented here. So first we prepare a shear thinning fluid using Dansangang. And this solution is purely shear thinning due to its rigid molecular structure. And then we prepare a polyacrylamide solution, which is viscoelastic, with a very similar flow curve to this liquid. So this solution is purely shear thinning, and this solution is both shear thinning and viscoelastic in order to disentangle the shear thinning effect. And then we prepare 2 Newtonian fluids at 2 end viscosities. This one is the 0 shear rate viscosity. This one is the infinite shear rate viscosity using glycerol solutions. So these are the data measured from the rotational rheometer. The circles are the data of Dansangang solution, and the field triangles are the data of the polyacrylamide solution. They have similar flow curve. And then we prepare 2 Newtonian solutions using glycerol solution. And in order to cover the dilute region, we also prepare another set of model fluids at higher concentration. And this is how our experimental setup looks like. So drops are released from this Lido and impact on a heated aluminum block, which is connected to a temperature controller and kept at 400 degrees Celsius. And high-speed camera is used to record the impact process. So this height gauge allows you to change the impact velocity. In other words, the impact vapor number. So results, the maximum bouncing height. So as you can see here that for the high viscosity glycerol drops, Dansangang and polyacrylamide drops, the data are almost consistent. And the only one which is different from the others is the low viscosity glycerol drops, which is the low viscosity Newtonian drops. And it starts to decrease after a critical vapor number. And if you look at the morphology, you see that there are some wavy structure on the drop surface for this low viscosity drops, but for all the other drops, the surface is quite smooth. And in order to look at this wavy structure more clearly, I inclined the camera to get a top view. So as you can see that during at the maximum spreading, there are some finger-like protrusions on the ring, and when it retracts, these fingers start to coalesce, and they create very strong long asymmetric flow, which induces the non-uniform mass distribution, and finally causes the drops to somersault during rebound. And this is side view. So, for example, this one is high viscosity drop, very symmetric rebound, and this is a rotating rebound for low viscosity drops. And we roughly estimated the rotational kinetic energy of the drop. And if we assume that this part of the energy is all transformed into the potential energy, so we can calculate delta H. And we add this delta H to the original data, this is what we get. So you can see that also the angular velocity increases as the Weber number goes up. So you can see that all the data becomes almost consistent, which means that the total kinetic energy is only partially transformed into the rotational kinetic energy rather than dissipated during the retraction phase of the low viscosity drops. And also long-Newtonian effects play little role here, as you can see from the previous result. And the main effect is due to the symmetry break during the retraction, which is observed only in the low viscosity drops. Second part is then we extend the Leidenfrost drop impact experiment to a specific fluid, long-Newtonian fluids called the viscoplastic fluid or the yield stress fluid. So it describes a soft matter which behave like a solid when the applied shear stress is below a critical value, and it starts to flow after this critical value is overcome. Here are some examples of the viscoplastic fluid. And what we're interested in, what would happen if the yield stress is comparable with the Laplace pressure. So ideally, it would be good to introduce a single dimensionless number, which is a product of a Bingham number and a capillary number, which expresses a competition between the yield stress and the Laplace pressure. But there are two issues with this single dimensionless number. First one is that the surface tension is still yield defined in the viscoplastic fluid, and secondly, the values, the yield stress value measured from, let's say, a rotational barometer is only a single component of the stress tensor. So this value might be different from the real value in the 3D experiment. And there are two independent mechanisms which may lead to the rebound of the Leidenfrost drop. The first one is the surface tension. So at maximum spreading, the drop tends to restore to its original spherical shape in order to minimize the surface energy. And the rapid release of this surface energy will result in an increase in the kinetic energy, and finally bounce off the surface. Also, some authors suggest that this might also be due to the elasticity of the compressible vapor frame, which is formed during the drop impact. So here you have a high pressure vapor layer, which provide upward forces for the drop impact, and finally cause the drop to rebound. And so in order to evaluate the contribution of the vapor layer, our experimental scheme is to conduct Leidenfrost drop impact experiments using viscoplastic drops. Viscoplastic fluids characterized by different magnitudes of yield stress. So here are the measured data from the rotational rheometer for couplable solutions. So we prepare in total 6 solutions, and they have different magnitudes of yield stress, and also different Bingham capillary number. And first, the impact morphology. So you can see that as the Bingham capillary number increases, which means the yield stress increases, you see that the maximum bouncing height of the drops goes down. And even at these very high Bingham capillary numbers, you can even see the unoblique bouncing and drops. So quantitatively, maximum bouncing height is a function of the Weber number. So for the low yield stress cases, it starts to go up as the impact Weber number increases. But for the Bingham capillary number higher than 1, it actually fluctuates around 1 value. And if you look at the minimum retracting diameter, which is the minimum diameter that is reached at the end of retraction, so for the high Bingham capillary number case, it actually increases as the Weber number grows, but for the lower yield stress cases, it decreases as the Weber number increases, which means that as the yield stress grows, the surface forces are no longer able to minimize the free surface of the drop, and the inertia deformation upon impact becomes permanent, resulting into an oblate bouncing drop. This can be expressed by the Bingham capillary number, which is a combination between the yield stress and the Laplace pressure. Also, the main contribution to the rebound behavior of Leiden's force drops is due to the surface forces rather than the intrinsic elasticity of the vapor cushion. Part 3, the impact of viscoplastic drops on viscoplastic surfaces. And so this actually originates from the 3D inkjet printing application. So in this case, you have a droplet of fresh material, which impact on a partly cured material, and they can be characterized by different magnitudes of yield stress. So our drop impact experiment scheme is to conduct viscoplastic drops impact on viscoplastic substrates, which are characterized by different magnitudes of yield stress. And this is how our experiment setup looks like for this case. So the drops are dyed with black ink, and here we replace the substrate with a transparent plastic box filled with model fluid. So here is the drops is viscoplastic drops, and the substrate is also viscoplastic. And for the image processing part, so here you can see that the black part is actually the crater, which is formed during impact, and the gray part is the drop fluid, because the drops are dyed with black ink. And here I used MATLAB to process the image and to capture both the profile of the drop fluid and the profile of the crater during impact. So both the dimensions of the crater, dimensions of the drop fluid are measured during impact. And this is how a typical drop impact process look like. So first, the drop fluid penetrates the substrate, and then a crater is formed, and the crater grows, and then it retracts and finally disappears. So this is the case for a low Weber number. This is the case for high Weber number. And here, an interesting phenomenon we observe is at the end of impact, the drop fluid actually is permanently lassoed in the substrate. As you can see that after a long time, this shape does not change, and this final shape varies for different impact parameters. And one important value parameter here is the volume of the drop fluid, which is under the interface, because this is also could be an indicator of the surface roughness in 3D inkjet printing. So here I calculated the volume of the final shape using image processing, and I introduced the single dimensionless number, which is the product of the yield stress ratio and the Weber number. The yield stress ratio is the yield stress of the drop to the yield stress of the substrate. And I identified two regions. So when this number is below a critical value, the normalized drop volume is below 1, which means that it's in the partial penetration regime, and after a critical value, it's fully penetrated. And this is the empirical equation I got. And also here, another interesting thing is that so we have both the profile of the drop fluid and the crater, which is formed during impact. And it would be interesting to fit our experiment data to a crater evolution model, which is proposed by Bisghini. So this is what we get. So for the drop fluid, so here the data point are experiments, and the solid lines are the model prediction, and also here for the crater. And you can see that it's actually better to describe the behavior of the drop fluid rather than the behavior of the crater, especially for the low Weber number cases. So the conclusions, the volumes of the rest of the drop fluid were calculated through image processing, and the single dimensions number was introduced to reduce the region map of behavior. Also, the crater model proposed by Biscayne is more suitable to describe the dimension of the drop fluid rather than the real crater. Finally, the drop impact on spherical soft surfaces. So I used the PDMS to manufacture the spherical soft surfaces. It's a common material that is used in microfluidics, for example, to manufacture the microchannels. And it's Young's modulus depending on the mixing ratio of the base and Curie engine. So I select 3 mixing ratios so that I have the substrates of different softness. For example, here is the hardest one, there is intermediate one, and here's the soft one. And here are some manufactured examples of my substrate. Different diameters, different mixing ratio, which means different Young's modulus, different softness. And the image processing again. So here I have a recorded image. First, I captured the profile of both the substrate and the drop fluid using image thresholding. And then I subtract the substrate from this one, and I get the profile of only the drop fluid. And then I color the drop fluid with blue and the substrate red, and I get the final image. So you can see that here how impact process look like. So, but firstly, impact on the loss pole, and then it spread, and then retract, and sitting on the top, and start to oscillate. And here I'm looking at some parameters. First one is the spreading angle, which is this angle, and also the length of the wetted arc, which is this one. And also the dynamic contact angles are measured. I adopted a new Lovo technique based on volumetric mask scheme to measure the dynamic contact angle. And this method can measure the dynamic contact angle on a curved surface, which is something that the conventional method cannot do. So for the spreading behavior, we observe that the effect of the curvature of the substrate and the elastic modulus of the substrate actually, the effect of these are negligible. You can see that they are almost consistent. However, for retraction, you can see that the red data is the data with the lowest diameter ratio, which means the highest curvature, and the drop actually retract more compared to the other data, except for this one with the lowest softness. And also we tried to use a theoretical model to estimate the how much energy is dissipated due to the deformation of the substrate. And we found that, for example, we use a simple energy balance approach. So here you have the energy dissipation due to the viscous force, and you have the energy dissipation due to the deformation of the substrate. And this solid line represents the prediction considering low dissipation. And this is the result considering only the dissipation due to the substrate deformation, and this is the result considering the energy dissipation due to the viscous forces. You can see that actually here the viscous dissipation still dominates. And we also use this, compare the model prediction to our experimental data for various impact parameter set. And also as I mentioned before, the dynamic contact angle are measured using a Lovo technique. You can see that, for example, here is the effect of the curvature. So as a curvature, so here is the diameter ratio increases, which means the curvature decreases. And you can see that the oscillation magnitude of the dynamic contact angle actually decreases as you increase this curvature. And the effect of the elastic modulus, if you can see that as the elastic modulus decreases, also the oscillation magnitude decreases. And the effect of the impact variable number, so if you have an increase in the impact Weibull number, the oscillation magnitude also decreases systematically. As conclusions, the drop impact impacting on a surface with a higher curvature are observed to experience a more prolonged retraction phase. And the dynamic contact angle was measured using a Lovo digital image processing screen based on a goleometric mask. Energy conservation approach accounting for the energy dissipation due to substrate deformation has been proposed. Here are some publications during my study. And I'd like to thank the UK Fluids Network for awarding me the thesis prize as a runners-up. And thank you for your attention. Thank you.
Time for questions. Yes, please.
In the first part of your talk, you mentioned like the impact of non-Newtonian, and you used the Carnot model. But from the picture, just
Which one?
before impacting them, not so spherical. Can you predict that? I mean,
You mean using the Carbopol solutions?
Yeah.
Yeah. Because it has a very high yield stress, so if you release it from the needle, right, if you have a very high yield stress fluid and it's released from the needle, so you push the fluid out of the needle, it has a, like, how do you say, this sausage shape of the droplet. Yeah, that's due to the yield stress nature of the fluid. Yeah. So if this yield stress is low, you can get a spherical shape.
Any questions? I had another one, which is you estimated the rotational kinetic energy.
Oh, this one,
Of
yeah.
the droplets.
Yeah, I consider this as a rigid body. Yeah, it's a very rough estimation, I know. But for example, maybe you have the secondary flows inside the drops, which also has kinetic energy, but it's a rough estimation.
Was it just from the pictures you see there?
Yeah.
What are you talking about when after it landed and it started to rotate? Is that where this estimate comes from?
Sorry, after it bounces off the surface, yeah, it starts to rotate. Yeah.
Not there. Oh,
Yeah.
okay. So that's really, if you like, a lower bound on how much energy is dissipated in that mode, right? Because what you said is it's probably going to dissipate more because of all the internal motion.
Yeah, probably more. Yeah.
Now, yes, to the back.
Just related, if you force rotation of the drop before it impacts, do you then expect it to bounce back and
Sorry, can you?
It's the retraction that then starts rotating, as I understand it, because of the
Symmetry break.
balance ability and symmetry break.
Yeah.
So but if you just had a drop that was rotating as it went down, that helps stabilize it, or would it be expanded?
In that case, but so after it impact on a surface, you mean when you release the drop,
Yeah.
you let it to rotate, right? And then I suppose the rotational kinetic energy will be dissipated during dropping impact, because if you have, let's say, a rotating drop and the impact on the surface, which the substrate will provide opposite forces, right, which reduce the rotational kinetic energy, right? So.
Yeah, I don't know. I just whether it was a way of overcoming this
Okay.
or not.
Other questions? Again, I have another one. This is all done for the Leidenfrost regime, is that
Yeah.
right? And so if you then allow wetting to occur, so you reduce the temperature, what do you think would change in the both in what you see and then in any analysis of it.
You mean reduce the temperature of the substrate? Right.
So you no longer have at the moment the droplets are beautifully separate from the substrate.
Mm-hmm.
But if
So you
they
mean
were to
the
actually-
droplet partially touches
Yeah,
the substrate, right?
yeah.
That would be interesting. Yeah. Because I'm studying in the Leidenfrost region.
Sure.
So yeah, I didn't change the temperature, which is 400 Celsius degree.
I'm just wondering what would happen. What would be the big change?
I don't know.
No, okay.
One quick question. Have you done any experiments where you get shear thickening behavior?
Sorry,
Have you done any experiments where you have complex fluids which exhibit shear thickening rather than
we tried to make some cornstarch solutions, yeah, but we found out that if it's difficult to generate a droplet using shear thickening
You
fluid.
say that, but Detlef Lozes shows some experiments where you get some very interesting...
Yeah, I know, and I read that paper. Yeah, but
So you said you can't reproduce those results?
yes, but actually, when I was in University of Liverpool, my project was to do drop impact experience using the shear thickening fluid. But then I did some literature review, and I found out that you need the density matching liquid, which is the chemicals are CS, something, yeah. And it's the university think that one is radioactive, and they stopped me to purchasing that chemical, yeah, because I want to get a uniform.
Did you say CS?
Yeah, CCS, yeah. CSCL, I think CSCL, yeah.
Okay.
It's a high density fluid solution, which people use it to mixing the cornstarch in order to get a uniform solution. Yeah.
Right. That sounds fun. Any other questions?
So you are using complex fluids here, and basically the viscosity is a function of shear rate, right?
Yeah.
So how you are characterizing the viscosity, like as some numbers like high viscosity as 72 millipascal?
Using
the same figure, like.
using the CY model.
So which viscosity you are referring there in the image, in that video?
Which one?
I mean the video which you are showing there. Like,
This one?
No, the previous one.
This one?
The drops which are impacting where it says like high viscosity 72 millipascal second.
This one?
Yeah. Here also you are saying like mu is.
Oh, okay, it's actually this one. Yeah. At this impact wave number.
So the viscosity when it is impacting the surface.
Yeah. No. It's a Newtonian fluid. Sorry.
Okay.
This one is a Newtonian fluid. This one is not shear.
Both the videos were for the Newtonian.
Yeah. Yeah, this one, both of them. But if you try with the shear thinning or the viscoelastic fluids, the process is almost similar, you know, because the overall viscosity is very high, so you get a symmetric bounce back. So this is only for the low viscosity drops, only observed. Yeah.
Because one more time.